In this video, we're going to use Euler's method in SageMathCloud. Euler's method is an algorithm to solve differential equations, at least approximately, given a differential equation in the form dy dx is some function of x and y, and given some initial starting point, x0, y0, on the solution curve. Euler's method will approximate the rest of the solution curve. It's based on the idea that this differential equation gives us the slope of the tangent line at any point, or the slope of the curve at any point in the plane. So starting at this initial given point, x0, y0, we're going to follow the tangent line along the tangent line that's given with this slope from the differential equation. We'll follow that tangent line some fixed distance to a point we'll call x1, y1. Since the solution curve is close to the tangent line, the x1, y1 point is almost on the solution curve. And then you repeat the process again. You start at x1, y1, use the differential equation to find the tangent line there. You follow it for a short distance to a new point, x2, y2, which is also close to the solution curve, and you keep on going. Repeat as many times as you want. The process is the same each time, so it's easy to iterate this formula on the computer. So let's see how we get from some point xn, yn. Let's say you repeat it n times, and you want to take the next step to get to xn plus 1, yn plus 1. So we start with this point. We find the tangent line there. So here's the general formula for a tangent line where our function is called y of x, and we're at some particular point x equals a. Here's our general tangent line formula we've seen many times before. In this particular case, a is x sub n, that's the given x value. Y of a is y sub n, that's the given y value. And the slope, y prime of a, is given by the differential equation. The differential equation says the dy dx, or the slope of y, is equal to the function f evaluated at the given x and y. So here we see right here, f of x sub n, y sub n, that's the slope. That's equal dy dx, the derivative, at the particular point x and y n. So I plugged y in place of the function value. I plugged this f in place of the slope, and I plugged x sub n in place of the specific x value. And so we get, that is our tangent line. Then we take xn plus 1, the new x coordinate, we plug that into the tangent line to get our new yn plus 1, and so yn plus 1 is y sub n plus the function times xn plus 1 minus x sub n. Now we're going to do this process so that this difference right here, x sub n plus 1 minus x sub n, is the same each time. That's what we're going to call the step size. I'm going to call that h. So in summary, here is Euler's formula. To move from one x coordinate to the next, you just add this step size h, which we're going to decide at the beginning. That's not going to change. And to get from one y value to the next, you take the old y value, you add on the function f, which is from the differential equation. So using the differential equation, you find the slope using the old x and y values. You multiply that slope by h, the same h that we moved in the horizontal direction. You add that quantity here to the y sub n. That gives you your new y. So let's do an example. I want to use Euler's method to approximate the solution curve of this differential equation, dy dx equals x times y. I want it to go through the particular point 0, 1, and I'm going to graph this from 0 to 2. Alright, I'm going to do this first off just by hand, and then we'll let the computer do it. So I'm going to use just 5 steps here at the beginning. So 5 steps to get from x equals 0 to x equals 2 means each step needs to be 2/5. So that's going to be h. I'm going to start with x sub 0 is 0 and y sub 0 is 1. That was the given point up here. I'm going to calculate the new x and y formulas using Euler's formula here. So I've arranged all these results in this table. So here's my initial point, 0, and then to get to the next x coordinate, I simply add the step size 2/5. So I add 2/5 and I get 2/5. Then you take 2/5 and add 2/5 and you get 4/5, 4/5 plus 2/5, 6/5 plus 2/5, 8/5 plus 2/5, and finally you've reached 2, which is where I want it to stop. That's the easy part. The y part, you start at the given y value, which is 1, and then you take, to get to the next one, you take the old y value, that's 1. You get the slope. Remember, the slope here is given by the differential equation. The slope is x times y. So I take my old x, that's 0. I take my old y, that's 1. I multiply by the step size, 2/5. And that's what the formula says. Old y plus the slope times step size. And that happens to turn out to be 1 again. Alright, to get to y2, I take my old y value, that's 1. I take my old x value, that's 2/5. I take my old y value, 1, multiply by h, and that gives me this one, 29/25. Next time, I take my old y value, 29/25. I add on the old x value, 4/5, times 29/25, that's the old y value, times the step size, 2/5, that doesn't change, and I get this thing, and so on. Now remember, this multiplying by the old x value, here it's 8/5 is old x, and this is the old y value. From there, the fact that I'm multiplying the old x times the old y is specific to this example. That right here, xn times yn, that's where the slope comes in. That comes from the differential equation. That's because this differential equation says the slope is x times y. That part will change in different examples depending on the differential equation. The other parts are the same. This h part stays the same throughout on both x and y. And then, of course, adding the old y just is taking the previous one. But the slope part will change when you have a different differential equation. Now I'm going to go ahead and plot these points just to see a picture of this solution curve. So here's the point command in Sage. You need parentheses for the point command. And I want to plot a list of points. So to do that, I can either use the point command over and over and over again, or I can just use it once and feed it a list. And to do that, I put square brackets, tell Sage that I have a list of points, and then I put in the ordered pairs, just as normal, separated by commas. And of course, you can change the size of the color and such, but I plotted the points. Now, if you wanted to just draw lines, I didn't do it, but you could connect the dots here with lines, and that would give you an approximation of the solution curve. So we can kind of see a little bit, looks like kind of an exponential looking thing here. Alright. Now 5 steps is not really enough to get a good approximation, so we'll use the computer and do many more steps. So I've set up these formulas to kind of do Euler's method. So I told Sage y is a variable. I defined the function f. That comes from the differential equation. In this particular example, it's x times y. In your assignment, there'll be different differential equations to type here. x0 is the starting point for the starting x value. That's given in the problem. That's 0. y0, also starting y value given in the problem. That was 1. x underscore n is what I gave the name to where I want to stop. Here I was going to graph from 0 to 2. So I start at 0 and stop at 2. N is how many points I want to calculate, the number of steps. So I want to calculate 50 here. And then Sage is going to automatically calculate the step size I need to get from x0 to xn in that number of steps. So these are the things that you can change. If you want to copy and paste this code, you can change the function according to the differential equation. I change these to the given x and y value, decide where you want to stop and how many steps you want. The rest of it you should just leave alone. It will automatically calculate the step size. I'm going to keep track of all the y's using a list. So I have the x list and the y list. This starts the list out with the initial value. This gets ready to keep track of all the points. So the first point I have is x0, y0. That was given in the problem. I'm going to call that P. As I go through this process, I'm going to add elements to x list and y list. I'm going to add additional points on to P. Okay, here's where I apply Euler's formula. I have this for loop. For I in range n just repeats the 2 lines below n times. So here n is 50, so it's going to do these two lines 50 times. Notice these lines are indented. That tells Sage that these two lines are within the for loop and they need to be repeated. Actually, there's 3 lines in the for loop, that one too. So first off, I'm going to add onto the x list. So I take x list bracket I. That's the current element in the x list. I add h onto that, so that's the step size. That gives me a new element for my x list. So I add that back into the x list. That appends it onto the end of the list. For y, I take my old y value, which is y list bracket I add on the function applied to that. That's the slope. That's the differential equation. Slope times step size follows the tangent line. Now I put this little RR here just to convert to a decimal. Otherwise, Sage can go really slow when it tries to keep exact values. So I convert this to a decimal here just to speed it up. Alright, so I have my new x, I have my new y. Now I'm ready to add the point on. So I took whatever p is, that's all the points I've done so far. I add a new point, x list I plus 1, y list I plus 1. That's the point I've just added. So I went from I to I plus 1. And then I add a line which connects the old one, I, and I plus 1 from the x and y lists. And I run that through n times. Here it's going to be 50. And finally, when I'm done, I just say show p. That will produce the graph. I built the graph up one point and one line at a time. So here's the solution curve that I get, the approximation here. Now here is a graph of my approximation, which we just had, along with the actual solution. This function is the actual solution curve here. If you solve this using separation of variables, for example, like we talked about in the last video. So e to the x squared over 2 is the actual solution. And you can see at the beginning, remember we start here at 0, 1. That point was given. So they agree exactly at the beginning. As you move away from that beginning point, the solution in red and the approximation from Euler's method in blue start to get further and further apart. So you can see by the time you get to 2, there's quite a gap between them. Here at the beginning, they're pretty close together. So closer you are to your starting point, the better, generally speaking, you'll be. Of course, we can make this approximation better by making n larger. That means you'll have a smaller step size, you'll take more steps. If we want to go past x equals 2, where I stopped, we can always change xn, and the further we go, the worse this is going to become. Now I set up this little interactive box here, which allows you to change xn and change n, and it will automatically update the graph. Now if this, on your notes, if it's not showing, if it says evaluate this cell to use this interact, you might need to click on the little arrow next to this line here, just off the screen, and it will show this, and then just run this one time, and it should automatically, once you run it once, it should automatically load every time you open this these notes up. Okay, so let's start by just adjusting n. So maybe instead of 50, let's do 100. Oop. So there is 100 points, and still stopping at 2. So you can see now there's not quite so much of a gap here between them. It's getting better. How about we go up to 200? And we'll wait for it to calculate. And now you can see we're starting to get so many dots that this blue line is almost all dots, but that's alright. Get a little wide. We can see that it's even closer now. The more steps you take, the better your approximation will be. Alright, let's go back to 50, and let's take this ending point out to 3. And we'll wait for this to update. Okay, so now the further we go in the x direction, away from our initial point. Our starting point here was 0, 1. The further we go away, the worse this approximation is going to become. Now we have quite a big gap here towards the end, and if I go up to 100, then it's going to get better, but still not perfect. And the further away you go, the larger n is going to need to be. Let's just boost it up to 500 and wait for it here to calculate. And now with 500 steps going from 0 to 3, pretty good. A little obscured just by the width of the dots here. You can see by the time you get to 3, it's not perfect, but it gets better and better. So I'll let you play around with that if you want to. Let me do another example. So we have this initial value problem. I'm given this differential equation that gives me the slope, y plus x. I have this given initial value, so this is the origin, the point 0, 0. I want to approximate y of 2. So it didn't ask me to graph anything, so I'm going to skip the graph part. I copied and pasted the formulas from above and just erased the plotting of the points and lines. So I changed the differential equation. It's now y plus x is my function that was given right here. My initial x value was 0. That's right here inside the function. That's the x input. The y sub 0 is also 0. That's the answer here. I want to approximate y of 2, so I'm going to stop at x equals 2. Right now I'll just use 50 and see what happens. And then the rest I can just leave. Now in the previous example I wanted to see the plot. Now I don't really want the plot. I just want to know what's y of 2. That's the last element in my y list. So the x list will stop at 2. The y list will stop at y of 2. And the last element here is actually y list bracket n. So that's what this does. Y list bracket n is the last point that you calculated. So in that case, it's going to be y of 2. And here's what we get. So this is my first approximation for y of 2, 4.1, when n is 50. Let's see what happens if we increase n. So I just changed n to 100. Everything else is the same. And now we get y of 2 is approximately 4.2 and change. Alright, now I'm curious what's the actual value here. So I solved the differential equation and just went ahead and used Sage. Told Sage y is a function of x. I used DE-solve to solve that differential equation with this initial condition specified right there. And here's the function it gave me, negative x plus e to the x minus 1. And I want to plug x equals 2 in there. I could have just put 2 in here in place of x, but I went ahead and defined a function in case I wanted to use this later. So I called it capital F, since I already used little f up above. So here's the actual solution, and then I plugged in 2. Here's the exact answer, e squared minus 3. Here's a decimal approximation from Sage. So y of 2, actually I should put approximately equal here. This is the actual answer rounded to whatever 15 decimal places. So almost 4.4. Remember my approximations were 4.1 and then 4.2, not quite there yet. So let's increase n one more time. I want to see if I can at least get this first decimal place. So I went ahead and boosted it up to 500, and here it is, 4.36 roughly. So here's kind of a summary of what I calculated. When n was 50, I got 4.1, n is 100, 4.2, n is 500, I got 4.359. Here's the actual answer, and as you can tell, as n gets bigger, this thing is getting closer and closer and closer to my correct answer. If you want several decimal places of accuracy, you can see that n has to be quite large here. Going from 0 to 2 in the x-axis is quite a big step, so you need lots of steps here to get a good approximation. Alright, so that's Euler's method, a way to approximate solutions of certain differential equations just using the tangent line.